What's up, everybody? Today I will show you how to use the second derivative test to determine whether a critical point corresponds to a local maximum, local minimum, or saddle point. To do that, the first thing we need to do is calculate for critical point, and we do that by setting derivative equal to 0 and solving for x and y. We have a function here that depends on x and y. So the first thing we're going to do is calculate the partial derivative of x and the partial derivative respect to y. And then we set both of them equal to 0. So the partial derivative respect to x will give us this expression, and the partial derivative respect to y will give us this expression. And we set both of them equal to 0. Okay, and let's try to solve it. We factor x. Okay, great. And then from here we see that we have two solutions. The first one will be x equal to 0, and the second one this. Okay, so we already see here x is 0, and if we look on the right side, let's solve for y. We get y equal negative 5x squared over 14 plus 1, right? And then we take this expression and we put it into this equation right here. And what do we get? Okay, so we see we have an equation that only has one variable. So let's go ahead and solve for x. X squared equal 140 over 6, and that is 70 over 3. So if we do the square roots, it's going to be plus or minus square root of 70 over 3, which is the same thing as square root of 210 over 3. It's the same thing, it's equivalent. I just prefer to only have like the radical on top and not on the bottom. And you can get that just by multiplying the top and the bottom by 3. Okay, great. So we see here that we already have like 3 values of x. So we have x equal to 0 from up here, and we have x equal to negative square root of 210 over 3, and x equal to square root of 210 over 3. So let's find the corresponding y's, and then we're going to use the equation right here. So if you plug x into that equation, you're going to end up getting y equal 1, negative 22 over 3, negative 22 over 3 as well. So these 3 points are our critical values. Okay, now that we have our 3 critical points, now we need to examine each of the points in order to determine like which one is a local max, local min, using the second derivative test. And let's look at what the second derivative test says. Okay, this is the criteria. Okay, so let's go ahead and find our second derivatives. So we already know that the partial derivative of x was, okay, so from here let's do the derivative of this expression respect to x. Okay, great. So this is what we have, and then we can do the same thing for the partial derivative of y. We know it is already. Okay, so let's find the partial derivative of this expression respect to y. So it's only giving us 14. Okay, so we're gonna take the expression, this expression right here, which is the partial derivative of x, but we're gonna take that derivative but respect to y. We are gonna get 10x. Now that we have these 3 elements, now we need to evaluate our critical point. So let's start with the first one, 0, 1. So we just plug it into this equation, and we are going to get negative 10. Same thing here. Fyy, it's 14 no matter what. So in that third one, you get 0. Okay, now that we have these three elements, we can now calculate d of 0, 1. And d of 0, 1, we get a negative 10, we multiply by 14 minus 0 square. So we're using the equation here. And then this gives us negative 140, which is less than 0. Okay, we see here, we look at the requirement, it's on the third bullet. It says if d is below 0, then the point is a saddle point. Okay, so therefore, we can directly conclude that 0.01 is a saddle point. Okay, so let's look at the other two critical points. Okay, we're gonna find, and then we are just gonna plug it into this equation, and we should be getting 560 over 3. And for fyy, we say no matter what, it's gonna be 14 because, right, it's not changing here. And we'll just 10 negative. Okay, great. Now that we have these three elements, we can find d. Multiply this minus, we square this. Okay, great. And if you put this into your calculator, you should be getting 280. Okay, we know 280 is a positive value. Okay, we look at the requirements. We found the first two bullets. So we need to look at the sign of fxx. So we see here, we see fxx also is greater than 0. So then we fall into the second bullet. It says that the point is a local minimum. So we say this point is a local minimum. Okay, so let's check the third one. And if you put this into the calculator in this equation again, what do we get? We get 560 over 3. And this one 14, we said, get 10 square root of 210 over 3. Okay, great. Now let's calculate d, and this is giving us 280, which is greater than 0, right? Again, we fall into the first two bullets, so we need to look at the sign of fxx. We see here it's greater than 0, so it falls into the second bullet, which means that the point is a local minimum. Local minimum. Okay, so do you see here that using the second derivative test, we were able to determine that this point was a saddle point, and this second point was a local minimum, and this was a local minimum. So we did not see any local maximum, and then we did not encounter the fourth case here, which is where the test is inconclusive. Thanks for watching the video. Please give us a thumbs up if you like it, and share with your friends, and please subscribe. Thank you.